Can any of you please confirm if you can see the screen?
Yes, sir.
Thank you. Okay. All right. So today we'll study one rather representation of finite states machine. So far you have represented finite states machines either using a bubble diagram kind of thing, the transition graph, or a table, a state transition table. But as we studied for the purpose of computer-aided synthesis, where a program actually synthesizes the circuit, sometimes this bubble diagram or the table is the table would be too big, actually would be not so important, so not so useful. So there is a slight modification of the transition graph that is used to specify or specify a circuit. We'll actually see that it's easy to convert this representation. So this is kind of an intermediate representation, some kind of intermediate representation, which a chart kind of thing, which is both understandable at a high level as well as can easily be converted into a Verilog or some languages. Okay, so this is called an algorithmic state machine or ASM chart. All right, so this is almost like a flowchart. It is almost like a flowchart. So what flowchart does is it shows a sequence of action and control flow of actions. It's almost like a flowchart, but along with these above things that there are actions and then control flow, you have a sequence or a timing available. Okay, and this basically we would use a flowchart. We'll use a flowchart to represent a sequential machine, the state diagram of a sequential machine. Okay, so this is a typical ASM chart. We'll explain the components. There are three main elements in an ASM chart. One is something called a state box. It's represented by a rectangle. The state box consists of the following. In the top, it would contain the state name. And inside the box, it would contain the register allocations. That means if you have a flip flop representing it, what are the values given to the output of the flip flop? Or it also represents some actions which are mode type. That means once you are in the state, not action, some outputs. Once you are in the state, you will get that output unconditionally on what the input is. If you are in that state, that's the output, unconditionally, irrespective of what the input is. So it's a mood type output. So all the mood type outputs are specified inside the box. Okay, and as it turns out, only the mood type inputs which are 1, only they are specified in the box. And also if there is some state assignment, some register assignment that are mentioned in the box, and in the top of the box, the state is given. You have only one data flow coming inside that. So this is an important term. So this flow is sometimes called a data flow kind of thing. It means that or rather you can also consider it as a flow. It consists of one value is written here. Then you have these diamonds. This is a decision box. There will be some logical condition, just like a flowchart, and depending on the output, suppose I have a binary decision, you take one of the output paths. So this is a conditional path. This expression is usually a condition on the inputs. It's because you are already in this state. Then you have a condition on the inputs. So you check the inputs depending on the value of the inputs. And finally, this output of this decision box may be connected to something called a conditional output box. So that means if we connect this followed by this followed by this, it would mean if you are in this state and the input is 0, let's say, then the output is this. So you have to be in a state and you have to get some particular input and then you get this output. So this is a conditional output or a melee type output. This might also be an action. That means you can update some values in the registers and so on. That can also be there. So this can be there. So the benefit of these three elements have over standard graphs or bubble diagrams is that you can do higher level specifications. We'll soon see that you can do higher level specifications. All right, so let's look at this. So individual component a little more detail. So this is the state box. This is equivalent to one node in the bubble diagram. The name of the state is written here. The outputs are written inside the box. Only output that must be set to 1 is written. If by default, if an output is not listed, it is set to 0. Sometimes in the top, if you have a state assignment, say 0, 0, 0 is the state assignment, that's also written in the top right of the box. Okay. This is a state. This is called a state box. So this is clear. It's basically, and it can have only one input coming in and only one output going out. So you have the state name, maybe the state assignment, the output signal, which are one once the system reaches this state. It's a mode type output, and if any action is to be taken, all other outputs are implicitly assumed to be zeros. Okay, so this decision box is indicated by a diamond shape used for a condition expression that must be tested, usually on the input value, input bits, input signals. You have an exit path. The condition is usually one or more of the inputs. Okay, sometimes there is a, just like C, you can just write W, means which is an implicit for W equals 1. This is a binary decision box. You can also have a vector decision box. Okay, denoted by an this kind of polygon thing. So you have a vector of input conditions. Let's say Z or Q naught. Okay, these are the input condition, and depending on what this bit vector does, you have possible outputs. Note that there may be don't care here also. You can also specify don't care if some bit combination is not mentioned. That's basically a don't care. Okay, so this is basically a multi-bit decision, or something you can also think of it like a case statement in C. Okay, so finally you have the conditional output box indicated with an oval shape. It's a melee type output, which means that if the system is in a state and there is some condition on the input, some input value is obtained, then you get this output. So it's a conditional output. Output depend on the state variable and the inputs. It also has a single input, single output, but the input usually comes from the output of another decision box. Okay, so this is a typical thing. So what can happen usually in any block except for the decision block, both the rectangle box and the square block, element, you have something called a register transfer. Register transfer or output. Okay, so this register transfer means like this. So this run means This is run is, let's say, an output variable. So you have a list of output variables which are set to 1 on reaching this box. Also, you can have this is a register transfer. This means some flip flop or some register is written a value 0. Okay, is written a value 0. So these actions are taken place. Now, usually these 3 boxes, with some of them being optional, these 3 boxes are connected in the following manner. So first, you have a state box. Okay. So there you have a state box name. Maybe you can have an assignment also. And then what are the register transfers happening? What are the outputs that are set to on? They are mentioned. Then the state box is single input, single output. You come inside the state box, you go out of the state box. But from one state, it is possible that in a FSM, from a state, you go to multiple other states. So how do you do that? So from state 1, you can go to either state 2 or state 3 or state 4, depending on what the input is. How do you do that? You do that by this decision box here. Okay, you do that by this decision box. So what happens in the decision box? So start is a variable. Start is an input variable. So initially it was in idle state. Then it checks the input variable start. If the value is 1, then it gives this output and maybe afterwards moves to another state. It gives this output. Note that the oval does not contain a state. Oval does not contain a state. Oval gives an output. What is the output? Or maybe some action. So here the output is PC is written a value 0. Some init output is given, and then maybe it moves to another state. Similarly, if start is 0, maybe it goes back to this state, idle state. Maybe this will loop back to idle state. Okay, so typically this state followed by a decision box followed by an oval output, conditional output. These 3 are typically connected this way. So they form a unit. These 3 connected like this form a unit. They basically describe one node in a state transition diagram. These 3 together represent one node in a state transition diagram. Okay. All right. So this basic combination of these 3 is called an ASM block. It's called a ASM block. So I have written this down as a enclosing square. This is called a ASM block. One ASM block will contain exactly one state, some decision boxes. Here there is one decision box. There can be more decision boxes. There can be nested decision boxes. Here is an example of a nested decision box. Okay, so it can contain multiple decision boxes, and the output path of each decision box, can give one conditional output. So here are 2 outputs. So it gives 2 conditional output. The action in the register transfer in the first output is R is incremented, and second output is R is reset. There may be some explicit outputs also, This is just a register transfer. There may be some outputs also. And then output of these conditional ovals, they can either go to another decision box or they can go out of this ASM block. Okay, so in here it goes out of it goes into another decision box. Here it goes out of the block. Okay, so this one state, 2 decision box and 2 conditional outputs, they constitute the ASM block. one single block representing one state in a state transition diagram, representing one state in a state transition diagram. Now, this output of this ASM block should go into another ASM block. And you can get an entry to a ASM block only to a state box. You can come inside a ASM block. You cannot directly go to a decision block or a conditional output block. You should come, the incoming path to ASM block should always terminate in a state box. Should always terminate. So you see this goes out, and they are all terminating this outgoing path, this outgoing path, this outgoing path. They are all terminating in a state box. Now, this state box is the same ASM block, it's looping back. This state box, maybe other state boxes may belong to two different other ASM blocks. Okay. All right. So this is the. So you see, this is kind of, we are representing the state transition diagram as kind of a flow chart, as kind of a flow that flow of events. So this happens, then this happens, then this. The difference between flow chart and ASM chart is that there is no timing sequence mentioned in the flow chart. In a normal C program or whatever program, software program you write, there is no sequence, timing sequence. Suppose you have two parallel paths, you don't really specify that when this will happen and when this will happen, or this will happen after this or not. Okay, so there is no timing mentioned. The additional information, since this represents a hardware, a circuit, in the additional information that's present in a ASM block is the timing diagram. Okay, so it also implicitly specifies that what is followed by what. So this happens, then this happens. What this basically means is that if you are in a state, you go out of the ASM block, you go out of an ASM block only at a clock cycle, only once in a clock cycle. So in the next, so either the falling edge or the rising edge, whatever your implementation is, only in the next edge of the clock cycle, you move out from one ASM block to the next ASM block. Whereas in a normal flowchart, it can be any time. So this, whenever the execution is over, it goes to the next element and so on. But here, this transition movement from one, because they represent states in a state transition diagram. You know that state transition happens only at the clock edges, if we design so. Okay, in a synchronous circuit. So here, this transition should happen only in the clock edges from one ASM block to the other. Also, see, there is one more thing to be noted, that what happens in one clock cycle? So the system will stay in one ASM block in a whole clock cycle. So what will happen in that whole clock cycle? First, it will move to this state, whatever the state assignments they will be attend. Then all these register transfers will happen in the same clock cycle. All this input checking will happen in the same clock cycle. And all the outputs, if there are some outputs that turned on, either unconditional or condition, mood type or melee type, all these outputs will happen in the same clock cycle. So in the same clock cycle, these states will attend. These inputs will be checked, these outputs will be given, all this register transfer will take, and in the next clock cycle, it will move to the next state. It will move to the next state. Okay, so this is just an example that we have given from this mal 1, mal 0. Let's see. So there is an idle state, and there are two other states, mal 0 and mal 1. So let's see, it's the leading clock cycle, that let's say that's what we consider. And this is the start state. So this is if you look at the states in which they are, you will see they will happen only at the clock cycles. They will happen only at the clock cycles. Okay. So basically, this ASM chart is a synchronous or clocked version of a flowchart. It's the clocked version of a flowchart. At every clock, you move from one block. That's why this block concept is there. This block basically means one clock cycle. One block means one clock cycle. So it moves from one clock cycle to the other. Okay, let's see some examples. Let's have some examples. In the right, so what we'll do now is that we'll convert some FSM diagram to their equivalent ASM chart. Okay, let's look at this FSM to the left. So we have three states. We have three states, A, B, and C. This Z is an unconditional output. That means moment you are in state A, Z becomes 0. Moment you are in state B, Z becomes 0. Moment you are in state C, Z becomes 0. Okay. So this Z is kind of a sequence detector. You are trying to detect a sequence, let's say 101 or something. Whenever you come to the end of the sequence, or you have detected that sequence, which is maybe the state C, then you get an output of 1. All right. And there are these state transition. There is no conditional output. There is only unconditional output. You could have had some conditional outputs also. And then W is an input. W is an input. And depending on the value of W, you go from one state to the other. You go from one state to the other. So at W, if you are in A and W is 0, you stay back in A. If you are A, W is 1, you go to B, and so on. Okay. So this is the transition diagram. So we now want to convert it to an ASM chart. As you can see that there are three states. So we will have three ASM blocks. Let me write down the ASM, show you there will be three ASM blocks. So this is my one ASM block corresponding to state A. This is my second ASM block corresponding to state B. And this is my third ASM block. Very simple. You just map one of the states to one block. Is my state C. Now I just complete the okay, and there is only one input variable. So moment I come out of A, if it happened so, if for both values of input you go from A to B, then this box would have been not there. But there are two different values, you go to two different states. So W is the input. Is the input. So you have a conditional block on the input. You check the value of input. So if you are in state A and input is 0, you go back to state A. If you are in state A in the first block and input is 1, you go to block B. Go to block B, you go to state B. Similarly, here, if you are in B and your input is 0, if you are in B and input is 0, you go back to state A. You go back to state A. If input is 1, you go to state C. Okay. Similarly, in state C, if input is 1, you loop back to self loop. If input is 0, you go back to state A. You go back to state A. Okay. So it's almost trivial to convert an ASM to an FSM to an ASM chart. In fact, it's also trivial to convert an ASM chart back to an FSM. Okay, all you need to do is that you need to just follow two steps. You need to identify the blocks, and once you identify the blocks, you put one state for one node in the diagram for one block. Find out the inputs, and depending on the inputs, you draw the arcs in the FSM diagram. You draw the arcs depending on the conditional boxes where they go, where their outputs go. One point to be noted in this regard is that it's a valid ASM chart. You can convert it to an FSM. If any, note that this is one constant that should be there. Just like while drawing a flowchart, you should have some constant. While drawing an ASM also, you should have some constant. Any ASM block should have only one incoming path, should have only one incoming path, should have one and only one incoming path. But it can have multiple outgoing path. It can have multiple outgoing path. But it has to have only one and one incoming path. Okay, so that's a rule you need to identify an ASM block. Okay, so here is another where you have a conditional output. Okay, you have a conditional output. So this is like this. So you have two states. You have two states. So you will have two blocks. This is one block, and this is one block. Sorry, I made it wrong. It should have only one input. So this is one block. Okay, and so you can come to A either from a reset, some reset state. You can come to A. All right. So now let's see. There is one input W. So you check on one input W, and then you move to other state. So that's how it's the flowchart, the ASM chart is written down. But note that the output is conditional. The output is not at a state. The output is on an input. The output is not on state, it's on input. So what this means is that you need a you need a conditional output block. So this is Z, a conditional output block. Okay. You need a conditional output block. So if you are in A, if W is 1, so note that as I have told before, only the outputs that are 1 that will be written. The 0 outputs will not be written. We have mentioned it here. Only the output that must be set to 1 is written. And the default if his output is not listed, either inside the rectangular box or inside the conditional oval, if the output is not 1, then it's not listed. All the non-listed outputs are 0, assumed to be 0. So you see, this output is not to be listed. This output is not to be listed. Only this output is to be listed. Only this output. And what is this output? If you are in B and you get a W of 1, you give an output of Z. See, Z equal to 1 is not written, just Z is listed. And then you go back to B. Self loop to B. Okay, so this is the ASM chart. Let's look at another one, which is a little bit more complex. All right, so you have 4 states. You have an ideal state. You have a GNT equal to 1 state, 2 state, 3 state. You have 2 states, 4 states together, and you have inputs R1, R2, R3. So this means that if you are in idle and if your R1 is 1, you go to GNT. From GNT, if R1 is 0, you go back to idle. Okay. And here what happens? You go into GNT 1 and then give an output of G1. Here you give an output of G2, here you give an output of G3. Okay. So how many ASM blocks will be there? Naturally, 4 states are there. There will be 4 ASM blocks. So you'll have 4 ASM blocks here. And how many? There are 3 inputs: R1, R2, R3. So you will have at least three diamonds, decision boxes. There is no output which is conditional on the input. So there is no. So you see, all the outputs are in the states. They are not on the transitions. They are not on the inputs. They are not on the arcs. So you will not have an oval conditional output box. You will not have an oval conditional output box. So let's see what are the ASM charts or ASM blocks. Note again that ASM block can only have one incoming path and may have multiple outgoing paths. So can you tell what are the ASM blocks here? So you see the first ASM block will be this thing. This is one ASM block. There are only one incoming. Sorry, this should be inside. This should be inside in here. And 3 outgoing, rather 4 outgoing paths. Okay, 4 outgoing paths. What is the second ASM block? This is the second ASM block. Similarly, this is the third ASM block, and this is the fourth ASM block. So these 3 ASM blocks, this is the input, and you have 2 output, this and this. These are the 2 outputs. Now let's see how this is a representation of this FSM diagram. You are in idle state. You are in idle state. If all 3 R1, R2, R1, R2, R3 are 0, you go back to idle state. You loop back to idle state. Okay, so R1 you check, then R2. So this is product of R1, R2, R3. So or all 3 of them should be 0. This followed by this, followed by this. All 3 are 0. You go back here. Now let's see what are the outgoing. You loop back. Outgoing, if R1 is 1, you go to GNT1. If R1 is 2, you go to GNT2. That means if R1 is 0 and R2 is 2. Okay, so this is the condition. R1 bar R2. So you see this is R1 bar R2. This is R1 bar R2 bar R3 bar. This is R1 bar R2 bar R3 bar. Okay, on these conditions they move here. Let's see what are the outgoing conditions from each of these GNT1 and GNT2, GNT3. If you are in GNT1, you give an, if you are in GNT1, this you have a unconditional output G1. You have an unconditional output G1 which is set to 1. Note that the only ones are listed, zeros are not listed. So G1 is 1, that is listed here inside the state box. And if it is R1 is 1, it loops back. If R1 bar, it loops back to idle. If R1 bar, it loops back to idle. Similarly here, R2 bar, it loops back to idle. R3 bar loops back to idle, either otherwise it self loops back. Okay, so this is the ASM chart. I think it is very easy. I mean, you can easily convert one to the other. In these examples, probably the benefit of the ASM chart is not very apparent. I just kept them simple so that you understand the conversion. But in more complex circuits, let's say you take a multiplier circuit or a divisor circuit or more complicated circuit which does blockwise operation, fairly complicated. You see, the FSMs are good for simple circuits like sequence detector or maybe full adder or things like that. But if you have a more complex circuit, for example, the double-double circuit, if you have such circuits which are more complex, and then the ASM is a better representation. It's like a flow chart. It's like a high-level language. So it's much easier to do that. You see, if you forget about the FSM diagram also, this is much more readable. This is much more readable. It's like a sequence. You do this, then check this, then go here, then check this, then go here, then check this. It's more like an algorithm. It's more like an algorithm. Okay, so this is a consistent effort. All the hardware designers, their specification, because see, finally it will do a job, it will do a task. So often it is easier to write down the tasks as an algorithm. Okay, so one of the, if you really look at is not toy examples, but really complicated designs, the initial specification will be like an algorithm. It will be like an algorithm, and that is much easily represented by the ASM chart rather than a FSM diagram. It's much easily represented by the ASM chart, and this ASM chart is further converted to no need to go back to FSM. It's converted directly to a Verilog. You can easily see that you can very easily convert it to a Verilog. You can write a Verilog program very easily out of it. And then the Verilog is converted, transferred to lower levels, register transfer level and further down levels till the geometry. Okay, so this ASM chart is a much better representation, much easier representation than the FSM. There is another advantage. All of design is modular now. So you design modules. So even till the very highest level, you have a power module, you have a timing module, you have a communication module in a mobile chip. So it's broken down into modules, and even within subsystems, they are broken down into modules. This ASM chart can very easily be broken down into modules. You have a it's like you have a part of a chart which is one module, part of chart which is another module. It is very easily broken down into modules. So that's the advantage. That's the advantage. So you can any modular design can easily be converted into ASM charts. That's the major advantage. In fact, there are electronic design automation tools where you can directly draw ASM charts from your specification, functional specification, and then they'll convert into Verilog statements and so on. Right. So with this, we come to the end of this class. Let me mention a few things. See, the thing is that with this, there is only one topic left, that is hazard. The only topic left is hazard. So, do you have some? So CRM, I'll not take the 9 to 10 class. I'll not take the 9 to 10 class. I'll close here. But CRM would like to take this hazard class sometimes in the evening. So are you free sometimes from 7 to 8 to take the class? Otherwise, we can record it and keep it for you also. Okay, so we'll put up an announcement that we'll have an extra class from today's 9 to 10 class. We'll have at 7 to 8. And what you can do there is to we will cover the hazard part. Otherwise, we'll record it also. If you are not available, you can see it. And tomorrow we'll just do some examples. So once this hazard part is covered, then we are done with the syllabus. And then we'll just do some examples for the remaining 2 classes. We'll review the entire course, what are the steps and what does it stand with respect to your next courses on computer organization and so on. What does this stand and how it is used in modern day, how these principles are used, actually practiced in modern day of digital design principles. Note that this digital design is still very active area, not just computers. There are many other systems that are designed. It's a very challenging area. So we'll discuss that and maybe we'll review the course in the next 2 classes. But today evening, 7 to 8, we'll have a special class by CRM on the hazards. And one more announcement is that